These are the LT3 notes for the electricity and magnetism unit. The purpose of this target is to calculate voltage, resistance, and current using Ohm's law. We will use Ohm's law the rest of the unit. This is going to be very basic, all right? So we aren't going to distinguish between series and parallel circuits like we will down in target 4. All right, that's where it gets a little fancier. This is just getting some basic rules down for how we do this. But before we do that, we would need to discuss what is this voltage, current, resistance. And so we'll start out with just some definitions. And voltage, think of that excuse me, as the electrical pressure, okay, the electrical pressure that pushes electrons through a circuit. So let's look at your cell phone as a circuit. What is providing the voltage? Like, what is pushing electrons through your wires? Because the electrons are actually in the wires. They are not from the voltage source. And what is making them go to the parts and the pieces of your phone that maybe create the vibration when you get a text alert, where your screen lights up so you can read your messages? All right, what is providing the push? And I think most of us know an example could be your battery. Okay, and a battery would provide electrical pressure. But not everything runs on a battery. Some things are plugged in. Well, it could be a generator, something like that, a power plant. Okay, that's pushing electrons. We're never in the business of making electrons. You buy your Duracells, you're not buying electrons. You're buying something that applies the pressure to push electrons through those wires. All right, so voltage, it's going to be represented by something that probably makes sense. So it's in volts, and so you're going to see it as the V. Speaking of those electrons, another essential part of a circuit would be the current, and that is just the flow of electrons through a circuit. Okay, so the flow of electrons through a circuit. So you've got your battery, let's say, that's pushing electrons through the wires of your cell phone, and current is measured in amperes. Nobody says that though. We just call them amps, and we will use the letter A. So it'll be like something has a current of 2 amps, for example. Now I haven't mentioned a VIR triangle yet, but on your formula sheet you have such a thing, and this makes your life extremely easy. All right, we're going to add some things here, but you may or may not be able to tell. Lighting's a little funny, but I stands for current. The letter I represents current in the VIR triangle. So voltage is the V, which makes perfect sense. Current is the I. All right, they don't use the C for it. I think it's because of a coulomb, and they don't want to kind of mix those two up. The third thing is resistance. Okay, we all know, kind of have a working knowledge of what resistance means. So if you go diving across the floor, friction would resist you, right? It would slow you down. So think of resistance as the friction that impedes, I-M-P-E-D-E-S, friction that impedes the flow of electrons. So it tries to slow them down as they're going through the circuit. And sometimes that's a good thing, because too many amps coming through a device would fry your device. All right, so there's a balance there, where we will intentionally install resistors in some circuits to slow them down. But if we get too much resistance and too much friction, we know that like rubbing your hands together too much creates heat. Too much heat, fire. All right, so this is something electricians really have to balance out. On the VIR triangle, R stands for resistance, which makes sense. The unit of measurement, so like we might see a current of 10 amps, so a 9-volt battery, is an ohm. An ohm is the Greek letter omega. It's that little guy. All right, so that's the unit of measurement for resistance. So on the VIR triangle, and I'll just try to read this through because I know it's hard to see. I would write down on the sheet the V is voltage, R is resistance, and I've got a picture of the little horseshoe here. I think it looks like a horseshoe, the ohm. And for I would make sure that you know it's an A for current. Okay, so I would write it down. You are not cheating if I'm telling you to write it down. That will help keep those all separate. Alright, so back to this resistance idea. We know it's just a type of friction. So let's talk about some ways that resistance can be increased or decreased. Let's think of ways to increase it right now. If you take a short wire and you replace it with a longer wire, so you increase the length. If we know that resistance is friction, just think about the amount of friction that you encounter walking from your locker to my classroom, and let's say you had to walk down a hallway that was twice as long. If it's longer, there's going to be more friction, you're going to bump into more people, your foot's going to interact with the floor, you're going to have more friction, more resistance the longer the hallway. Okay? Same thing with wires. So I think most of us are wise enough to know that our house is not wired on one continuous loop. You've got lots of little circuit breakers or fuses if it's an older house, and that's because you can't get too long of a wire or we get too much resistance. Too much resistance, too much thermal energy, bad things happen. All right, so that would be one way that we try to balance this idea of resistance. What if, we'll keep with the going up here, we're talking resistance, what if we placed a thicker wire with a thinner wire? So what if we went ahead and decreased the diameter of the wiring? Think about this. This is kind of far-fetched, but it always works for my head. If we have a fire truck, all right, think about the tank on that thing. Think about the size of a fire hose. So, you know, firefighters, they got to be able to get a lot of water out really quick to try to save buildings. Well, what if you put a garden hose on that fire truck? That water is going to have a heck of a time trying to get out of that hose. So that's what I mean. It's going to face a lot of resistance due to that smaller diameter. Think about the senior hallway trying to get down to the science hallway here. Okay, what if we made that hallway half as wide? Okay, so we're going to squeeze those walls in. My gosh, you're going to bump shoulders and have a heck of a time getting through there. All right, so a thinner wire, more resistance. If you have a heat blanket at home, that's how those things work. They put little tiny wires inside of your heat blanket, and when you plug it in, you have your 120 volts is the push from your outlets at home. 120 volts of push, and those electrons trying to get through those wires, that's how you're getting the thermal energy created in that heat blanket. So, fun fact, hopefully. And another way to increase the resistance is to increase the temperature. And that's what's tricky. So, let's say that the electrician that wired your house had an oops. They didn't pay attention in their electrician course, and these wires start to get hot. Well, if they start to get hot, it generates more resistance because those electrons start to bounce around a lot. Well, when things bounce around a lot, you get a lot of friction. And then you get a greater temperature. Like this is serious trouble. Because the hotter it gets, the more resistance. The more resistance, the hotter it gets. And eventually, hopefully the circuit breaker will blow, a lot of people say. Hopefully the fuse will blow, whatever. Do something to stop the current or you're going to have a fire. So those are three ways that resistance can be altered. So length of the wire, diameter of the wire, and then just temperature within. So to the math. These problems are very simple. We talked about this VIR triangle. It is on your formula sheet. For right now, if you don't have your formula sheet, hopefully you do. But we can draw it here. And there's a rule, and you won't know what it means right now, but it will make sense in a second. Cover up what you are solving for. This is one of the easiest things you'll ever do in a physics class, is this VIR triangle. So we have a divide, and a multiply. We know V is voltage. We know that I is current, which are the amps. And we know that R, the horseshoes, are the ohms, right? Okay, so you have a practice sheet. This should be on Moodle. Okay, if you're in class getting it, then obviously you got a copy of it. But this target, I'm going to keep it real simple. It's just going to be quick little stories, or sentences, not even really stories, where you pick out the numbers and figure out what you're solving for. So number 1 says a current of 3.7 amps is running through a circuit, and there's a resistance of 1.5 ohms. You're solving for voltage. The process here is to always write out the problem and write it out as VIR. Every time, no exceptions. VIR. And in this problem, it says a current of 3.7 amps. So my current is 3.7. It's a resistance of 1.5 ohms. So my R is 1.5. Then it says, what is the voltage? That's my question mark. That's where hopefully this makes sense now. Cover up for what you are solving for. This is one of those times my fat thumbs are helpful in my life. I'm going to cover up voltage because that is what I want to know. So I think you see where I'm going with this. What is left? Current multiplied by resistance. So we're going to go 3.7 multiplied by 1.5. We get 5.55, which we know in Moodle, we would enter that as 5.6. We would round to the 10th. So 5.6 volts. We wouldn't type the letter into Moodle. Those are the units. 5.6 is the answer. I'm going to give you another one where we're solving for something different. So it's number 3 in the practice problems. Number 3 says, if the battery in a circuit is 24 volts, resistance is 12 ohms, what is the current? VIR, always the first step. And it said the battery is 24 volts. It says the resistance is 3 ohms. What is the current? That is our question mark, then is I. We cover up what we are solving for. So this time I'm going to cover up that. Voltage divided by resistance. Number 1 mistake. People sometimes will go resistance divided by voltage. You never type that number in first, ever. It's always voltage first. So in this case, it's 24 divided by 3. And last time I learned my multiplication facts, that would be 8. And the units are amps, but we would just type in the 8. And we will solve for resistance. Just looking for what one I have left. So let's solve for resistance. So here we go. I've got a battery of 12 volts. This is number 7 on the practice. We have a current of 2.7 amps, solving for resistance. So for number 7, VIR. So the voltage is 12. The current is 2.7. And the resistance is our question mark. Covering up what we want to find. So cover all this stuff up. Voltage divided by current. So it's 12 divided by 2.7. I don't know what that is. 12 divided by 2.7. 4 point, and then a 4 is repeating. We'll round to the 10th, which means we keep that 4 after the decimal. Answer is 4.4 ohms. But you would just type in 4.4. Now, as I mentioned earlier, we're going to get a bit fancier with this, but this is very basic because we have to be able to use this triangle before we can distinguish between series parallel. So this is absolutely essential that you can run this. Alrighty, good luck.